2.1 Basic Set Concepts. In this chapter, you're going to learn how to identify basic sets and the concepts on how to manipulate them. What we do is we look at the sets and we try to see if it has a relationship. The elements contained in a set, is it equal to or is it equivalent to another set? These are things to be determined as we move along in this chapter. All right, so let's take a look at the methods of representing sets. So we have three different types of descriptions for describing sets or representing sets. All right, so for the first one, this is called a word description. And it says set P is the set of the first 5 presidents of the United States. So this is called a word description. We're just using words to describe our set. The second option is to list our set of elements. So this one has set P, this is meaning set P is equal to braces, Washington, comma, Adams, comma, Jefferson, comma, Madison, comma, Monroe, close with the brace. This is called the roster method. So the roster method is just as if like you're naming off a team roster and you're just listing each of the players. Okay, and the third option is set builder notation. So let's look at this example they have here. It says set W is equal to, and then the braces again, X such that. All right, so it's a set of X for all elements. The X is a day of the week. All right, that's a little fancy, if you will. What I'm going to do is rewrite using that same first 5 presidents of the United States that we used on the first example, and let me rewrite it in set builder notation. So I'm going to say set P is equal to, and use my braces, and then I'll have X such that, that vertical line means such that, and we'll just rewrite part of this. It's just like the word description. X is one of the first 5 presidents. We need to be specific about where these presidents come from. So I'll put of the United States. And I lost my spacing there, so I'll put it right below. And then we end with braces. So the set builder notation is a little bit of a combination between roster and word description. The new part on there for you is this vertical line, which means such that. So that is the 3 set notations that we'll be using. Word description, roster method, set builder notation. This slide here is just giving you 2 different examples of word description, roster method, and set builder notation. So we'll just talk about the first one, and you can review the second one on your own. The first one for word description, it says B is the set of members of the Beatles in 1963. All right, so that is your word description. Remember, we're just using words to describe our set B. The second one is B is equal to, and it has the listing of the members of the Beatles from 1963. And that's your roster method when you list each individual member. The third one is to list it in set builder notation. B is equal to all values for X such that X was a member of the Beatles in 1963. All right, so these are good examples for you to remember the 3 listings: word description, roster method, or set builder notation to describe a set. So this problem is asking us to determine if the collection is not well defined and therefore is not a set. So my understanding just from that first sentence is in order to have a set, it must be well defined. So it's asking us to look at this, determine whether this is not well defined. The collection of the 5 best NHL players. And you can see that we already have someone who gave us an answer here. It says the collection is not well defined, and therefore it is not a set. All right. One of the key things in this one that makes it not well defined is, take a look at this comment here. What is the definition of best? Now, the 5 best NHL players may be different from individual to individual. Like your opinion is going to be different than my opinion versus someone else's opinion. So therefore, it is not well defined. And therefore not a set. All right, so for this problem, it is asking us to express the set using the roster method. So remember that the roster method means we have to list everything out. What they started us out with is set builder notation right here. But there's some funny looking symbols in there that I think we need to review. All right, so we have X such that X, and then we have this funny looking, there it is. It looks like an E. So this is an element of. What that means is an element of. And then the bold N, let's see if I can make a bold N. That is representing natural numbers. If you remember our natural numbers, that's the set of natural numbers. Let me put that up here. All right, so let's take a look at that one more time. X such that X is an element of the natural numbers and X is less than 3. So if you recall, our natural numbers started with the number 1 and it just increased from there with an ellipse, dot, dot, dot. That is the set of natural numbers there. But for this case here, they want us, it says, and X is less than 3. So less than 3 means we do not include 3. So what's less than 3 is just the number 1 and the number 2. So the answer for this one would be D, and it's the roster method with 1 and 2 listed. So it must satisfy both conditions. It's a natural number and it is less than 3. We have a definition called the empty set. And it says the empty set, also called the null set, is a set that contains no elements. The set that contains no elements. And they use the empty set as the braces, or if you use the 0 with a slash through it, that's called your null set, which means the same thing. It is a set that contains no elements. So let's take a look at example 4 here. It says, which of the following is the empty set? Which of the following is the empty set? So if you took a look at A, it has braces with 0 in it. And since it has an element in it, 0, the number 0, it's not empty. It contains an element. So that's not an empty set. If you look at B, it just has 0. It's not even in set notation. So we can't say it is a set, an empty set, because it's not even in set notation. If we take a look at C, all values for X such that X is a number less than 4 or greater than 10. So can you think of a number less than 4 or a number that's greater than 10? I bet you can. And if you can, that means that is an element of that description. So therefore that set is not empty. All right, and the last one here. X such that X is a square with exactly 3 sides. So do we have a square that will have exactly 3 sides? No, that is impossible. So the D here is the one that has the empty set. Write that down. This one is my empty set. Right? And the empty set is just empty braces, or you can use the 0 with the slash through it. Let's take a look at this next problem. It says determine if the set is the empty set. Again, it is in set builder notation, and it says all values for x such that x is less than 6 and x is greater than 12. All right, so is this an empty set or is it not an empty set? So the thing you have to remember here is when it's and, it has to satisfy both conditions. Remember on that last one we had an and, it was a natural number and less than 3. Well, this one's asking you to be a number less than 6 and also greater than 12 at the same time. And since that is not possible, this set is the empty set. So be careful with the word and, it has to satisfy both conditions. All right, so these are definitions also. You've already reviewed one of them. It says the notation and it has that funny looking E. And now it has that E with a little slash through it. So it says the symbol, the E, is used to indicate is an element of a set. Remember that is an element of. All right, is an element of. And the one that has the E with the slash through it means is not an element of. All right, not an element of. All right, let's take a look at the reading below this. It says, because R is an element of the set, A, B, C, D, it goes on all the way through Z, the statement R is an element of that set is true. All right, so that right-hand side is just listing the letters of the alphabet. It doesn't have to visually be present for you to say it's an element of. It is assumed that it's continuous from C all the way through to the end letter Z. All right, it says observe that an element can belong to a set in roster notation when 3 dots appear, even though the element is not listed. So the same thing that I just mentioned. All right, so for this one, it's saying because 7 is not an element of the set, 7 is obviously not an element of this listed roster method, 1, 2, 3, 4, 5. It says that the statement 7 is not an element of the set 1, 2, 3, 4, 5 is considered a true statement. So this is a true statement. And on the second one, it says, because the set containing A is a set, that's this part here, and the set containing A is not an element of the set containing AB, then we have this statement. The set containing A is an element of the set containing AB. This is a false statement. For us to rewrite it so that it is a true statement, we would write something like the element A, right? The stands for is an element of. So A is an element of the set containing AB. That would be reasonable and a true statement. Or you can say something like the set containing A is not an element of the set containing AB. And that would also be considered a true statement. Our next problem says to determine whether the given statement is true or false. 5 is not an element of 1, 2, 3, comma, dot, dot, dot to 33. 5 is not an element of that set. And if we were to list that set out a little bit further, we know that it has natural numbers starting with 1 and that it gradually increases. So eventually we're going to get to that number 5. So 5 is actually an element of that set. So saying that it is not an element makes this a false statement. Recall the set of natural numbers uses that bold N is equal to, and we list with braces. In roster notation, 1, 2, 3, and you go on dot, 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 ellipse from there. So that's the set of natural numbers. And example 6 is asking us to express each of the following sets using the roster method. So in this case here, for part A, it's saying set A is a set of natural numbers less than 5. All right, so set A, so I'm going to put set A, is the set of natural numbers. So I'm going to start with the number 1 that is less than 5. So I'm going to list 1, 2, 3, and 4. These are all the numbers that are natural numbers less than 5. Right, then we'll take a look at part B right here. It says set B is the set of natural numbers greater than or equal to. Greater than or equal to. This equal to part is really important. Equal to means I can actually start with the number 25. All right, so it's saying set B is a natural number greater than or equal to 25. So 25 and greater. I'm going to list at least 3 numbers. You can list more if you like, and put my ellipse, and it goes on indefinitely. All right, and then for C, it says set E is equal to X such that X is a natural number and X is even. So we're a natural number and we are even. So set E, and I will list a few even numbers. We're a natural number, so we're greater, 1 or greater, and even. And again, this continues on this pattern. So I will put an ellipse and close with a brace. All right, so these are different types of sets, learning how to list in roster notation, given the fact that you are working with a natural number. This table here is listing the inequality notations and what the sets look like in set builder notation and roster method. So for this one here, it says X is less than A. So for the set builder notation, it says X is a natural number and X is less than 4. And in roster notation, that means you would put it as braces 1, 2, 3, and close your braces out. So you can go through each one of these. When you're using the less than or equal to or the greater than equal to, that means you can actually use the number that it's referring to. X is less than or equal to 4. That means we're going to include the number 4. Same thing down here. X is greater than or equal to A. So greater than or equal to 4 means we're going to use 4 and include it in our roster notation. So if we have less than or greater than, you do not include that value A, whatever that value may be. If it says less than or equal to or greater than or equal to, you include that value. These are examples of compound inequalities where you have 2 symbols, inequality symbols being used in your statement. So this first one has A is less than X, which is less than B. And A and B are just some values. So our example in set builder notation is X such that X is a natural number and 4 is less than X, which is less than 8. So that means we cannot include the number 4 and we cannot include the number 8 because we do not have that greater than or equal to or less than or equal to symbol. So therefore, since we cannot include those numbers, we're going to come out with roster method of 5, 6, 7. All right. And this next one, notice that they are using less than or equal to X, less than or equal to B. So since we have the equal to part on both ends of that X, or opposite sides there, that means A and B will be included. So once again, this is 4 is less than or equal to X, which is less than or equal to 8. And because of that, we are going to include the number 4 and the number 8 in our roster method. Sometimes on a compound inequality, you may have where you're only using one of the less than or greater than or equal to. And sometimes you just have less than or greater than. So be very careful. What this statement is telling you, A is less than or equal to X, which is less than B. That means with the value A will be included because it has that equal to part. The B has the less than, so it is not included in your roster method. So 4, remember we're looking at natural numbers, 4 is less than or equal to X, which is less than 8. So once again, because it has the equal to part, we're going to include the number 4, but we are not going to include the number 8. And the same thing with this last one here. It has the less than or equal to with the 8 and just less than with the 4. So we will include 8 because it contains the less than or equal to, which allows us to use the 8. Again, these are called compound inequalities. Let me write that last one in case it's too small for some of you to see. All right. We have a new definition here. It says the number of elements in a set. The number of elements in a set is called the cardinal number or the cardinality of the set. So the number of elements means you're going to count how many items are included in that set. So the answer when it says the cardinality, it should be a value. All right, and it says the symbol that in this N parentheses capital A and close parentheses is read N of A. N of A, or the cardinality of A. All right, so again, the cardinality is the number of elements in a set. And it says repeating elements in a set neither adds new elements to the set, nor does it change its cardinality. So they gave you an example down here. It says set A contains 3, 5, 7. Set B contains 3, 5, 5, 7, 7, 7. All right, so if we're asking for the cardinality of A, N of A is cardinality of set A, they're asking you how many elements in a set. So this one contains 1, 2, 3 elements. All right, so the cardinality is 3. If I am looking at the cardinality for set B, the number of elements in a set, I'm going to count each unique one. I have a 3, a 5, and a 7. So once again, I have a cardinality of 3. So it says you're looking at distinct elements. So don't count the repeats on the cardinality, just each unique item or value. For example 8, it is asking us to determine the set's cardinal number. So for part A, set A has the elements 7, 9, 11, 13. So I would say the cardinality of set A is 4. There are 4 elements contained in set A. If I take a look at set B here, I have B is equal to the set that contains 0. So the cardinality of set B is just one element. It contains one element. Looking at C, set C is equal to, and it has 13, 14, 15, ... 23, 22 to 23. So it starts from 13 and it ends at 23. If you were to list that all together, you would count out the number of elements. So the cardinality, the number of elements in set C, and you count that out, you should come up with 11 elements. Okay, and then on part D, let me see if I can get a different color in here. So for D, we have the null set. And if you remember, the null set is the same thing as the empty set, meaning that it contains no elements, right? Write this down. Contains 0 elements. So if I'm asking for the cardinality of the null set, I'm going to say it's 0. It contains 0 elements. Find the cardinal number for the set A. And we have it listed in set builder notation. A is equivalent to X such that X is a letter in the word waiter. Remember, this is set builder notation. So let's change that to roster notation and see what we come up with. So set A, roster means we're going to list, is a letter in the word waiter. So I will just put each unique letter down. Oops, that comma in there. All right, and it's asking you to find the cardinality of set A. So what we need to do is go in and count each one. I have 1, 2, 3, 4, 5, 6 elements. So the cardinality would be the number 6. And I can place that up in this answer here in the box. All right, so sometimes it helps to change your listing from the set builder notation to roster notation so that you can count your elements and answer the problem correctly. Find the cardinal number for the set. C is equal to all values for X such that X is less than 4 and X is greater than or equal to 11. So if you recall on one of the problems we practiced previously, the and was very important, this word and. So it has to satisfy both conditions. Is there a number less than 4 and also a number that's greater than or equal to 11 and it's the same number and it satisfies both conditions? The answer is no. So what happens is in roster method form, this will give you the empty set. There are no elements or numbers that are less than 4 and at the same time greater than or equal to 11. That's an empty set. So if we're looking at the cardinality for set C, the answer will be 0 because there are no elements that satisfy that. The next concept we're going to discuss is finite sets versus infinite sets. So this definition says set A is a finite set if the cardinality of A is equal to 0. That is, A is the empty set. Let's look at that one more time. Set A is called a finite set if the cardinality is equal to 0, or it's equal to the empty set. And then it says, or the cardinality of A is a natural number. So for it to be a finite set, the cardinality can be 0 or a natural number. And it says a set whose cardinality is not 0 or a natural number is called an infinite set. All right, so if we want to think of just some examples, if I gave you set A is equal to, and I just gave you empty braces, well, the cardinality for set A, is equal to 0. So that's considered a finite set. If I gave you another example, set B contains a few elements, and we have the cardinality of set B. In this case, there are 3 unique elements. So if it is a natural number, the number 3 is a natural number. This is also called a finite set. Let me give you one more example. If I gave you set C is equal to, and let's just say the set of natural numbers. All right, and I asked you to find the cardinality of C. we wouldn't be able to find it because the cardinality is not 0 and it's not a natural number. There are too many elements for us to count. And with this ellipse over here, that's indicating that it goes on forever. So we can never finish counting. All right, so the cardinality in this case does not exist. It is not 0. And it is not a natural number. I'll put that bold N here for natural number. So therefore, this is infinite. This is an infinite set. It goes on forever. Determine whether the set is infinite or finite. This says all values for x such that x is an element of the natural numbers and x is less than or equal to 20 million. So if I wanted to list this in roster notation, I know that my natural numbers start with the number 1. And I can add a few numbers here. And then we'll do our ellipse. And then it says x is less than or equal to 20 million. So I'll put a comma here, and then I'll put my 20 million. Less than or equal to. The equal to part means we're going to include that 20 million. All right. Now, it would take a long time for us to count how many elements in here, but you could determine the cardinality. You could be able to count each of the elements. So therefore, this is called a finite set. Remember, the definition of a finite set is if the cardinality is 0 or if it's a natural number. In this case here, you have many elements, but it is countable. If you can count the elements, it is a finite set. For this problem, it's asking us to express a set using set builder notation, use inequality notation to express the condition x must meet in order to be a member of the set. So they give us the set that starts with 30 and it goes to 31, 32, 33, and then there's an ellipse on there. So we know that these numbers that are listed are part of the natural number set. So for set builder notation, I would say braces all values for x such that x is an element of the natural numbers. We know that much. And if you take a look at the condition on there, since it includes 30, I can say x is greater than or equal to 30. And then it's just a matter of matching the correct answer here. So it looks like D would be the one that satisfies my conditions. All right, a new definition here. It says set A is equivalent. It's talking about equivalent sets here. Set A is equivalent to set B means that the set A and set B contain the same number of elements. The same number of elements is referring to the cardinality. So for the sets to be equivalent, the cardinality has to be the same. And they give you an example here. They have set A, x, such that x is a vowel. And set B, all values of x such that x is a natural number. And it is 3 less than or equal to x, which is less than or equal to 7. Remember, those symbols mean that we're going to include 3 and we'll include 7 in our roster notation. So they have the listing here for each one. These arrows are just meaning that they get paired with exactly one element from the other set. So A is paired with element 3 from the second set, and E is paired with 4, and so forth. And if you read this paragraph, it tells you just a little bit more about that. All right, so we say that when an element, each element from one set can be paired with exactly one element from the other set, it is considered a one-to-one correspondence. And basically what you need to know is that for sets to be equivalent, the cardinality has to be equal. The cardinality is not equal, they're not equivalent. It is simple as that. We just reviewed the definition for equivalent sets. Equivalent sets have the same cardinality. Now we're going to take a look at equality of sets or equal sets. So set A is equal to set B means that set A and set B contain the same exact elements. Both have the same exact elements, and it says regardless of the order, so they can be out of order on master notation, or possible repetition of elements. So regardless of order or possible repetition of the elements, if they have the exact same elements, they are considered equal. All right, let's take a look at this example. It says set A contains the elements W, X, Y, Z. Set B contains the elements Z, Y, W, X. Because they have the exact same letters or the exact same elements, these are considered equal sets. All right, and also in this case, if we were to find the cardinality of A, in this case, how many elements? There are 4, right? And the cardinality of set B, let me fix that. So the cardinality of B also 4. Since the cardinalities are the same, these sets are also considered equivalent. All right, and something to keep in mind here. It says if 2 sets are equal, then they must be equivalent. But the opposite of that is not true. If 2 sets are equivalent, it doesn't mean they are equal. For instance, I can show you a set A that can be 1, 2, 3, and I can do set B, which is A, B, C. So in this case here, the cardinality of set A would be 3 elements. The cardinality of set B is also 3. So in this case, these are considered equivalent sets, but not equal. They are not equal because they do not contain the exact same elements. So this is just another example for you to take a look at. Answer the following questions about the given sets. Are the sets equivalent? Explain. When we think about the word equivalent, we need to consider finding the cardinality for each of the sets. So looking at set A, we want to find the cardinality of set A. Cardinality again is each unique element. So I have a 5, 6, and a 7. So my cardinality is 3. My cardinality for set B, I have a 7, 6, and a 5. So this is also 3 unique or distinct elements. So since the cardinalities are equal, these sets are considered equivalent. So we need to find the matching answer for what we just said. The sets are equivalent because the cardinalities are equal. That would be answer B as in beta. Right? The next question states, are the sets equal? All right, so the condition for equal sets was that they need to contain the exact same elements regardless of order or repetition. So if you take a look at the 2 sets, they both have the number 5, the number 6, and the number 7. Set A has repeated elements, but they are of the same elements that are contained in set B. So what we're going to do is look through our reading and see if we can find out where it says, let's see, the sets are equal because set A contains the exact same elements as set B. That would be the letter B here that matches that. All right, the first one, it says the sets are equal because the cardinalities are equal. That goes back to equivalency, so that would not be considered. And then the third one says the sets are not equal because set A contains the exact same elements as set B. And that does not make sense. And the last one, the sets are not equal because the cardinalities are not equal. And again, the cardinalities have nothing to do with equal. All right, so through process of elimination, the answer is B. Example 10 says determine whether sets are equal. Determine whether each statement is true or false. And for part A, it says the set containing 489 is equal to the set containing 894. And we know that as long as they have the same elements and order does not matter, that these are considered to be equal. So this is a true statement. And it has the solution down here. All right. And then part B, the set containing 135 is equal to the set containing 0, 135. They do not have the exact same elements, so therefore this is a false answer. These are not equal sets. So once again, for equal sets, it has to contain the same elements regardless of order or repetition. A study of 900 working women showed that their feelings changed throughout the day. The line graph shows 15 different times in a day and the average level of happiness for the women at each time. Based on the information given on the graph, represent the set using the roster notation or roster method. So our set is all values for X such that X is the time of the day when the average level of happiness is 1. So if you take a look at this line graph, we have a title, the average level of happiness at different times of the day. We have each axis is labeled the time of the day, and then we have the average level of happiness. And we want to find where the average level of happiness is equal to 1. So here is my number 1. Let me highlight that. This is my rating of 1. And we want to take a look all the way across horizontally to see where does that match up at. And it matches right here. That's 1. This is this point right here. Again, there's another one that has a 1, and this has a rating of 1 also. So when we take a look at the times of the day, we have 10 o'clock, 15, and 16. All right, so they want us to list this in roster notation. It says set using roster notation or roster method. So we're just going to have those numbers listed, 10, 15, and 16. And that would be answer D as in Delta. So in roster method format, the times of the day would be 10, 15, and 16. Determine whether each statement is true or false. If the statement is false, make the necessary change or changes to produce a true statement. So our statement is some sets that can be written in set builder notation cannot be written in roster form. And we went over an example like this one. And this one happens again to be giving us an answer of B, but let's check the answer B and see what it says. It says that it's true. Some sets cannot be put into a list and still include all the elements of the set. All right, so something simple on an example, if I said all values for X such that X is an element of natural numbers and X is greater than or equal to 21. So there's my set builder notation, and it says that, let's see if we can put this in roster form. All right, so in roster form, I would say my set starts with the number 1 because it's a natural number, but I want numbers greater than or equal to 21. So we would start with 21 because it has to satisfy both conditions. These are natural numbers and they are greater than or equal to 21. All right, so I cannot list that totally in roster notation. This is what it would look like in roster notation, but I cannot include all the elements. because of that ellipse. This concludes the lecture for 2.1.